Hello. I'm Ryan Black. We're going to take a look at digital audio and what it is, what it actually is. How does it relate to analog audio? What's going on? So, first thing is, well, what is analog? And analog is a continuously changing voltage. But where does that continually changing voltage come from? It comes from pressure waves, sound waves in the air. And generally, we use something like a microphone, which is a transducer, to convert from one form of energy, the pressure waves in the air, into another form of energy, the actual voltage changes that then go down a cable. In audio, we often will save these in an analog fashion historically. And the two primary ones that you know, that I know, that you might still utilize are tape, analog tape, and vinyl, actual records. And there are various types of records. There were also cylinders and other forms that people utilized over the years. But those two are ones you should understand. And what a continuously changing voltage means is it's smooth. There's no point where it isn't continuous to the point before it. No matter how far you zoom in on the signal, it's still a continuous line. An analog waveform will look something like this waveform on the left there. And if we take a look at actually what this looks like on a record, it's crazy. It looks like that. And that is the actual etching, like stone tablets of audio information. And if someone just handed you this or handed an alien species this, like, what would they do? They'd be like, I don't know, maybe it's a topographical map. What the heck? Why would they put all these little grooves on a piece of shellac or vinyl? And so, but that's what it is. And what you're seeing there is the two channels, the left and right channels, that are modified by the voltage and etched into a disc. And then on the back end, what we do to hear this music is we take that signal and convert it back into voltages and convert that and amplify it to move a speaker, which then is also a transducer, and that converts the voltage energy into pressure waves. And an entire audio system can exist in analog. But most of us use digital. So what's going on? What is the change that happens from this analog thing into this digital thing? And you might have seen it in that little graphic I just showed. But digital is a way of encoding analog data so that we can manipulate it in computers with big calculators. That's all it is. That's the analog to digital conversion. And how we do that conversion matters. And I'm going to give you a brief overview of the two primary components that affect sound quality very directly when you do an analog to digital conversion. The first thing we're going to mention here is sample rate. And sample rate is how often you take a measurement of the incoming voltage. So when we look at this waveform, now looking at the right side here, you see that the voltage, this diagram showing voltage, is changing, right? That voltage goes up and then it comes back down. And this could be far more complex as a waveform, but in the digital format, we only have zeros and ones. So we're defining values in a stair-step pattern that we can record, literally like an Excel spreadsheet. You have a point in time, point number 1, and it has a value. Point number 2, and it has a value. That's what we do. And how often we do that every second will affect the frequency range of the incoming audio signal. We'll come back to that. But that is the primary component that our sample rate is going to affect with something called the Nyquist theorem. Now, what is important about that, coming back here, is that we need to have some standards, right? If you have a computer and it's expecting to see a certain number of samples per second and you read it back at a different rate, it will actually change the pitch of the audio. Maybe you've experienced this in a DAW. So the standard for audio on a CD is 44.1 kilohertz, or 44,100 times a second that we sample the incoming audio, or that we record a value of the voltage. That's a really important number to remember. 44.1 thousand hertz. Hertz being how many times we sample in a second, a rate. For video, we often use 48 kilohertz, 48,000 times a second. And that's a lot of times a second to sample an incoming value, right? I mean, that's very fast. But there, as I mentioned, is a second component to this. After sampling, well, it does determine the frequency response of the audio, but each value that we sample has a certain resolution. If you sample 44,000 times a second, but there's only two options, you're going to get an audio signal that goes, and that's it, because it can only choose a 0 or a 1 for every second. Well, we want more than that, right? We want to be able to choose all sorts of different values so that our digital waveform at least approximates the original analog waveform. So every sample has to choose a value, which is encoded usually in an 8-bit system, but or 24-bit or 16-bit, something like that. You might have heard of like 8-bit music and things of that nature. That's referring to the bit depth, which is often called quantizing of the values of each sample. So here, for example, you can see that just generically, we have 1, 2, 3, 4, 5, okay, 6, 7, 8, 9, 10, 11, maybe 12 total values. Well, that's still not that much. And that won't approximate a complex waveform in its changes in all the little variations which would relate to higher frequency. So we have quantizing, and the quantizing is an assigned value to the amplitude of each of those samples. More values is more accuracy to the original analog signal. The bit depth determines the number of possible values. And once again, to use our CD as a common place to go back to, a CD is 16-bit, which is 2 to the 16th power. Which is 65,536 different values. So 65,536 is the number of options available on each sample in a CD. And if you think about that, you have a huge grid now. You have sample rate along the bottom, and you have bit depth along sample rate and time, how many times a second we sample. Those dotted lines are sample rate. And you have amplitude on the y-axis, which is our bit depth. Those two concepts, sample rate and bit depth, are key to understanding analog to digital conversion, the quality of digital audio, and also the inverse process of digital to analog conversion, which we then hear through pressure waves. So a more densely, a higher bit depth is going to give us a higher resolution of potential amplitudes. And a higher sample rate is going to allow us to get little options in between every one of these points. And once again, more analogous to the original signal. So when you see things like this on the top, that is a digital representation of a waveform. And when we reduce the bit depth, you will see, in this case, literally that we just lose data. The difference between 65,536, which is the bit depth of a 16-bit system, and 8-bit, which only has 256 options, is massive, right? It's 256 times more resolution because this is an exponential curve. Cool. So that's the first key steps of this. Now I'm going to go into a little more detail on what we mean by Nyquist theorem and frequency. And here it is. The Nyquist theorem is the sampling rate, or the sampling rate must be twice the highest frequency that you want to hear. So if you want to be able to record the entire range of human hearing up to around 20,000 hertz, you need a sample rate that goes up to 40,000 hertz. Now, there are some studies that show that small children can hear up to about 22,000 hertz. Thus, we have a sample rate of 44,100, little extra, hertz. And that's the sample rate for a CD. It's designed to be able to reproduce up to 22,050 hertz. So the sample rate of 10,000 hertz would give us a highest frequency of what? No, figure it out. I can't hear you. Did you figure it out? 10,000 hertz sample rate, the highest frequency would be 5,000 hertz, according to Nyquist theorem. Sample rate equals 2 times the highest frequency. So if you had the highest frequency, if you had an audio file and you're like, you know what, my grandpa, he can't hear anyway, so he can only hear up to like, I don't know, maybe 8,000 hertz, your sample rate could be 16,000, and it wouldn't statistically make a difference. There's, you know, arguments about whether it actually does or does not make a difference, but arguably that's it. So that's your sample rate. Now, let's take a deeper dive into our dynamic range, which is determined by our bit depth. As I mentioned, an 8-bit system, like old computer games and a lot of music, people like using bit depth modifiers and stuff now. 8-bit has 256 steps in each sample. That gives us a value of 48 decibels of dynamic range. Well, that is pretty bad. That means the dynamic range is significantly less than the dynamic range of our hearing. Now, with that being said, most popular music from the last 30 years, 25 at least, is slammed where there isn't that much dynamic range. In real life, analog life, the dynamic range is relatively huge. Though in general, our human lifestyle, living around electronics and air conditioning systems and stuff, is much louder than it maybe was for our ancestors. When we increase our bit depth to 16-bit, the resolution of a CD, we then end up with 65,536 options, which, if you're doing the math and interested, this is 2 to the 8th power. This is 2 to the 16th power. I'll probably do a separate video on why that is. And you'll notice that that is not just a doubling to go from here to here, right? It is significantly more. It is, in fact, 256 times more. That's pretty cool. And that gives us 96 decibels, which is pretty much the range of human hearing. We as humans can't, something that sounds very, very quiet to us is around 50 decibels. 0 decibels is not silent. It's just a amount of waveform that the human ear does not, an amount of pressure variation the human ear does not react to. And so forth. So if we go up to 24-bit, we now have 16,777,216 values, which is 144 decibels, which is more than the human range of hearing. Human range of hearing is about 120 decibels technically, just like our frequency range of hearing is around 30 hertz to about 20,000 hertz. Really, it's more like 30 to like 16 to 18. With many folks today who use like in-ear headphones and stuff, it's probably lower than that. But as you can see here, our range of hearing is about 120 decibels. That's like your ears are breaking to as silent where you're like, this is creepily silent. So 24-bit will definitely give us range well above our range of hearing as far as amplitude is concerned. And that's great for things that are quiet, like reverb tails, things in the background, details that you don't so much hear as your brain has a reaction to. And there's some, studies and stuff that show that matters, that even if the average listener can't tell the difference between 24-bit and 16-bit, they can tell that they're different, right? They don't know how to qualify it as a audio professional might, where they're like, well, this has more clarity to the low end and I like the reverb tails. Like, if you don't know what all those things are, you can just go like, well, yeah, I guess they're different, which that's what people do. So in digital audio, we have sampling, as I mentioned, on that x-axis, and we have quantization or bit depth on the y-axis. And that determines our dynamic range for the quantization, and the sampling determines our frequency response, according to the Nyquist theorem. I don't know that this is actually that important to the entire slide here, but the top part I do want to draw your attention to. Red Book standard is the CD standard, and that is 16-bit 44.1. I would recommend on a recording platform to do a minimum of 24-bit 44.1 kilohertz as your standard. That would be my recommendation. And if you do that, you will have some high quality audio that can be processed and use modern plugins and all the details of that in your mixing process, which is great. So to review some key concepts from this walkthrough: sample rate, bit depth, what they modify or what they affect directly in an audio signal, which is sample rate affects frequency range according to the Nyquist theorem. Bit depth affects amplitude. It affects the dynamic range. Red Book standard or CD standard are the same term, and that standard is 44.1 kilohertz as the sample rate, 16-bit as the bit depth. I would recommend recording at least at 44.1 kilohertz sample rate and 24-bit bit depth as a standard. Most DAWs will do that without issue. Those are sort of the key ideas behind digital audio and how we get from analog to digital into the computer, back out from digital to analog to your speakers and into your ears to make music like this. Like so. And that was I don't know. Have you met Miss Jones? There we go. Until next time, talk to you soon. Do something cool every day.